Hi everyone, I like to walk. I prefer that as opposed to stand behind the podium. So I hope there's no camera here. Um, so one thing you're not going to hear from me is the word blockchain. Uh, my work isn't in that space, but I think it's quite relevant. And I think that's perhaps the reason why I was invited here to begin with. Uh, my focus is on digital twinning and specifically on how we do that for the built environment. But before I jump straight into that, just a few things about the place I come from, the University of Cambridge. If you've ever been there, it's a very nice, also touristic location to come and visit our old colleges, Corpus Christi, King's, Trinity. This is a very famous location. This is an actual descendant of Isaac Newton's apple tree. And that window in the back is Isaac Newton's office. I've been there once inside. Um, Speaking of Isaac Newton, the university is affiliated with a lot of very well-known individuals from Niels Bohr to George Stokes to John Maynard Keynes, Alan Turing, John Harvard, our recently departed Stephen Hawking, and several, royalties and actors and actresses. You probably recognize the faces in the bottom more than the faces in the top. Our facility is called the Civil Engineering Building, very boring name, and it looks just as boring as a facility, nothing like Cambridge, to be honest, because this building could be anywhere on the planet, right? There is no particular architecture here that would make it look like, yes, this looks like Cambridge. But it kind of shows how architecture is converging around the world into building structures that are not area specific anymore, right? And just focusing on something that just works for everybody. So enough of that introduction. Jumping straight into the topic, when we want to talk about the built environment, we're looking at economic infrastructure, we're looking at social infrastructure, we're looking at the interface with the natural environment. And within that space, digital twins are at the core. They're at the core because of the promise, the potential. And what's the potential? Well, it's basically better information management can help us do better, perform better across all the key performance indicators in cost, time, quality, safety, sustainability. But the challenge is that this is still a promise, and we haven't quite made that a reality. So what's holding us back? Why is it not a reality yet? Well, one reason is that if I was to ask each and every one of you to give me a definition of a digital twin, you'll probably give me a slightly different definition than everybody else, right? We still haven't quite gotten to a point where we understand what that really means. And so I've started to work with colleagues almost at a philosophical level to understand what really is this concept about. And we came up with this very interesting way of thinking. When you are just a young kid, let's say 1 year old, and you're learning how to walk, you take a step, it's in the wrong place. As a result, you fall. That is painful. So you get data from the world back to your brain saying, ouch, I shouldn't repeat that again, right? You then process that in your mind. What might I do different next time so that I don't have the same outcome? Because I didn't get to where I wanted and it was painful. So I make a new plan. I look at all the bad options in my head. I let them die in my head and I keep the best possible prediction and I make that step next time, hoping that this time I'm not going to fall, right? So this is the body-brain integration. The same thing happens in engineering. You have the physical asset, the body, and you have your planned asset, which is the brain, or more specifically, the prefrontal cortex, which is what boys don't have until the age of 25. Okay? Within that space, we do exactly the same thing. We monitor the asset, we produce some data, we interpret that into knowledge, we then use that to drive decisions and produce the necessary instructions to act upon and then get into impact. So far, I haven't told you anything new. All of you know this. This is not news to anyone, but it might be useful to help us frame the conversation. Um, Digital twins, they're called twins for a reason. They're not called triplets or quadruplets. Twins comes out of the word two. So what is the two? Well, the two is the physical twin and the digital twin. But let's say we had, I don't know if we have any twins in the room. If we have two human twins, they are not a system. They are two independent human beings, and there are no arrows between them. In this case, between the twins, we have arrows, and those arrows make it a system. So all of this is the twin system. And it's important to start getting our terminology right, because if we're not getting our terminology right, we have a hard time communicating about what we mean. Now that we've established that, why do we want digital twins? It's because we want to increase automation to manage increasing asset complexity. It's because we want to finally combine the product and the process, the modeling, the simulation, and the monitoring, the whole ecosystem in the same platform. However, by doing that, we create something that is complex and expensive to design, to construct, to maintain, to operate, but at the same time, significantly rich and therefore valuable, flexible, able to serve multiple purposes. We're also building things that are now federated, right? We're no longer in the world where we can go to a client and say, remember this model you had? We're going to scrap that now, and we're just going to put something completely new. That's not going to work anymore, right? We have to build on top rather than continuously refresh what already exists in practice. And building on top requires federation. In terms of extensibility and future-proofing, I like to give the example of the car industry. Back in the late 1980s, early 1990s, Lee Iacocca, I think was the CEO of Chrysler at the time, made almost like a joke about Microsoft Windows because they were being contested. Why is the car industry not performing as well as the software industry? And he said, well, if we were like Microsoft Windows, every car would fail every 3 miles and you'd have to restart it. But if you fast forward 20 years after that, and ever since then, that's exactly what the car industry has done. Cars are now computers. They're now sensors on wheels. Car companies are becoming data companies. Mercedes is selling data to the Dutch government, to the Swedish government, and they're coming to the UK also, and we're working with us trying to sell data to the UK government, right? We are just the drivers. We're just the poor drivers collecting data for them. So for them to accomplish that, going back to future proofing, they had to change something about the car. If the car is no longer a mechanical device, but a computer, the life cycle of the car becomes the life cycle of a computer. Back in those times, cars could last 15, 20 years. These days, cars are built to last 5 to 10 years, not unlike a computer out there. However, we cannot do that for infrastructure. We just cannot replicate that example. If you have a big project like Thames Tideway in London, which is a huge concrete sewer pipe that's built for 200 years, how many generations of technology is that pipe going to see? Right? We cannot possibly say, I will reduce the life cycle of the physical asset to match the life cycle of my digital asset. I have to find a way to make the same physical asset adapt to multiple generations of digital assets that support it. And of course, scalability, I think that's quite straightforward, but I'm spending too long. I have to move on. I've been told I only have 20 minutes and I already lost half my time. We need digital twins because we need to get to better decisions faster. We need a faster refresh rate so we can trust the information more. We need the ability to serve multiple processes and, most importantly, to achieve more automation. Leave the high-level decisions to the humans, push the low-level decisions to the subconscious, to the cloud. A good example of this is autonomous cars. An autonomous car is a twin system. It has a brain and a body, It collects data, it makes its own decisions, and drives the vehicle. And the whole process is low level enough these days that it can do that without human intervention, right? Or at least that's where we're heading. We're trying to achieve the same within our cortex. So if digital twins are so amazing, why aren't they as ubiquitous as physical twins? Why don't we have them everywhere? I got a few reasons here. First of all, we know the physical twin as a product and process, but we're still discovering the digital twin as a product and process. And we need to do a lot more R&D to make that jump. The second bit is that the owners understand the value of a physical twin, but not really the value of a digital twin. And this is why we need to build exemplar use cases to achieve rapid market penetration. And I'm having discussions with Jack, with Calvin, with other people about building these kinds of exemplars to showcase to everyone what is the potential, what are the costs to build that, what is the value, and drive adoption as a result. But last but not least, a lot of vendors are presenting incremental solutions as groundbreaking for obvious reasons. And as a result, that accelerates digital twins into the trough of disillusionment. So some of the work I've done to better think of a roadmap to that final action is to try to work with colleagues like Raphael Sachs at Technion and understand that full potential of a digital twin. And this is one of the figures from one of the papers we published, looking at the example of think of like a human standing in front of a lake. The human's the physical twin. The reflection of the human on the lake is the digital twin. So you have here physical product and process. You have here information volume. And as you go across the timeline, you have your planning and design processes at conception, producing the digital counterpart, which is planning and design, product and process information. Once you hit construction, here's your birth, prefabrication starts, prefabricated parts come to life, construction processes. Eventually you reach the weaning stage. That's when you leave the mothership, you go to site and you start assembling things, and you build your child physical twin from nothing into an adult, while at the same time you are producing construction phase product and process information, and so on and so on. I think the rest is self-explanatory. The key points to make here is that while the physical twin at some point might stop growing, it's like humans, we stop growing at some point, we're not getting any higher. The digital twin will not continue to grow. And this is also like humans. Our brains keep becoming wiser. We learn more over time, although our bodies are not changing. In fact, our bodies are becoming worse, but the same thing with the physical asset. And at the same time, we have to put things in context. A lot of people still don't understand the difference between a BIM file and a digital twin. That's your BIM file, right? The little yellow line containing design phase product information that is static at one point in time. And if you're lucky, you will also have a design status model with the design phase status information, the process data, or an S-built BIM file with your construction phase product data, or a project status model with your construction phase process data, and so on. And most of these tend to sit in different software platforms that may or may not talk to each other. Only now we're getting a few platforms able to kind of put that together, but not entirely, only across some of the platforms. What we definitely cannot do that is this part. That's what we cannot do. We're not yet at the point where our assets are dynamic, where every single property has a time function associated with it. So we can record what happens from the beginning of the asset lifecycle all the way to the end. We're just not built around that. And I think that's very, very important. Some other basic fundamentals. Digital twins are not made out of data. If we start throwing data into a digital twin, we will blow it up too much. Digital twins should be made out of information that is processed data, what is interesting from the data, and then further processed to derive information patterns via interpolation and produce knowledge. and to derive insight via extrapolation. All of these are perfect AI use cases, and this is why AI has a significant role to play within the digital twins ecosystem. Not just in terms of operating the system, but also in building it and designing it and every aspect of it. And another slide I really want to draw your attention on, because I end up focusing more and more on this, is this one. We already understand planning, design, construction, maintenance, and operation for the physical asset. We know how to do that. We have standards and regulations and hundreds of years of experience. We don't have that for the digital twin. How do you plan a digital twin? How do you plan the scope, the feasibility, and the costs of it? We don't have the tools yet. We don't have the standards. We cannot go to an owner, a large client, and say, this is the process, right? And this is what you need to ask from your customer. How do you design a digital twin? How you derive the digital twin asset class? Think of hospitals, roads, prisons, and so on. Design the appropriate data structures and cloud architectures to make that work. And perhaps blockchain has a role to play right here. Although I promised not to mention the word, but I've broken that promise now. Under data construction, how do you populate that class and derive a specific asset instance? In other words, how do I take this physical building and make a digital representation of it, very accurate one, and put it in that data structure? How do I maintain this over time? Because if I don't maintain this, then it becomes like the digital twin of Singapore, something we want to avoid. And last but not least, the top four are just costs. All of these cost money. The last one is the one that provides the value. And that's the one where we want to be able to build multiple vertical applications on top and derive as much value as possible. If you want to think of it like the road infrastructure systems, we already do all of this for roads, right? And then we allow for any car to drive on top and drive economic value. We want to do the same. We're building data infrastructure, and we want to allow the private sector to come in on top and drive economic value out of that. I only have 2 minutes left, and I'm just in the introduction, so I will have to really speed up for the rest. A lot of the work we've done in Cambridge is to try to achieve some of these bits. One of these is on constructing digital twins, and very briefly, it's the ability to go out there, scan an asset, get its points and pixels, derive its geometry, objects, and so on, and then map textures on top, detect defects, other problems, and create as accurate representation as possible. I'll very quickly skip through multiple slides that show how we've done some work on that. We've done a lot of work on step one, capturing the geometry, filling the gaps, equalizing the densities, also helping the person who's actually doing the capturing, right? And capturing multiple modalities at the same time, LiDAR, RGB, thermal, IMU, and so on. And as we're capturing that, provide real-time error information so that the person who is scanning can see what he needs to do and get better data. The thinking here is that you don't leave the site until everything is of the quality that you have in mind. So I think this is shown in this part of the video. Real-time accuracy predictions. As you walk around the site, we can find that accuracy and help you to do multiple loop closures so that you can get back to green on all of your data. Again, very little time. In terms of generating the actual geometry, that's a big problem, right? I have an example here, this reactor building 40 billion points in the point cloud. It took 10 people 6 months to make one model. That doesn't work. It works for a nuclear facility. It's not going to work for a typical highway overpass. And we need to build the types of methods that help us detect these components. This is a case for bridges. And then directly from that data, automatically capture the components, put them in place, and make the model. And again, we want to do that for real assets. that have all kinds of skews and peculiarities. In the real world, no bridge deck is straight, no pier is straight, and we have to be able to capture that reliably. So going from these points and pixels to objects to a model without a human intervention. We've done the same for buildings, going from the points, detecting floors and rooms, and then from the floors and rooms, detecting walls, fitting the components, and creating the final model. We've done the same for industrial facilities, together with Aviva, BP, and other companies, capturing all the MEP systems, connecting the various components, and building a connected mechanical system in addition to the structural system, again, without human intervention. And we've then added additional data on top, such as condition data. This is an example on bridges, capturing all the problems on the textures, measuring them and mapping them as properties back to the model. Or on a road, this is actually quite an old project, using your parking camera, capturing cracks, patches, potholes, and other issues, and then automatically measuring that and putting it back to the model. This is what Mercedes is selling now, 10 years later, right? This is commercial now. Bringing the sensor data in and collecting and tethering and monitoring to the asset so that we can see in real time what the feedback loop is, all towards the target of building the national digital twin. And I think I'm going to stop here because I'm over time already, and highlight this particular slide. I've worked in the UK together with the National Digital Twin Program since 2017 to allow us to expand that thinking to all of the UK. It's not an easy problem to solve, right? It's quite a challenging problem to solve because it has so many levels of complexity. But it is a viable program because from a government perspective, just like we have physical infrastructure, we also need to build our digital infrastructure to drive economic activity on board. Next year, I'm going to be on sabbatical in this part of the world, as I've told some of you, and I want to try to drive that thinking also here. How can we build this type of scale of thinking in Hong Kong, in China, in other parts of the world, because it is necessary to drive further economic activity. And this sector needs it much more than the car industry, because the car industry has big enough companies that can drive this on their own. This sector does not have that. And that's where government can provide a lot of value. I'll stop there. Thank you very much.